Okay, to get into our next unit, okay, it's entitled Redox Reactions. And in chemistry, we like to classify reactions according to what's being passed. For example, in a Bronsted reaction, remember, was the hydrogen ions were passed. In a redox reaction, it's electrons that are being passed. Okay? I would estimate that about 80% of the reactions in your body are redox reactions, so they really are very important. Now, notice in the example I show you, X wants to pass an electron to Y. Let's say we make X pass the electron through a wire. We now have electrochemistry, which will be the last part of this unit also. Okay, to show you how the redox reactions work, I want to show you one in more detail than you ever have to know, and that is iron reacting with oxygen to form iron oxide. This reaction has been studied in great detail because it's kind of important in our modern society, because what is iron oxide? It's rust. So a lot has gone into trying to figure out how you can stop this reaction, how you can stop iron from rusting. Now, I've shown below this what my X-ray eyes see when I look at this reaction. So let me share this with you. When I look at an iron atom, I see a nucleus with 26 protons and whizzing around 26 electrons. Now, you probably could have figured that yourself by looking at the periodic table, but that's actually what I see. When I see a molecule of oxygen, I see two oxygen atoms with 8 protons in the nucleus and 8 electrons floating around. Again, you probably could have figured this out yourself by looking at the table. Now, here's the part I have to tell you what my eyes see. In the compound iron oxide, the iron still has 26 protons. At better, it wouldn't be iron anymore. But the interesting thing is it only has 22 electrons. Ooh, okay? And the oxygen atoms still have the 8 protons, but they each have 10 electrons. Now, the way we summarize that is we say iron went from a 0 oxidation state to a positive 4. Can you kind of see where the positive 4 comes from? It lost 4 electrons. And we say that the oxygen went from a 0 oxidation state because it's neutral to a negative 2. Why? Because it picked up 2 extra electrons. Now, here's how the terminology works. Look at the line scale on the right-hand side. When an element goes up in state, we call that oxidation. So the iron went from 0 to plus 4. You don't care what the actual numbers are, it's just the direction that counts. So it's going upward, that's oxidation. Now here's the one that always made sense to me. If an element goes down in state, it's reduced in state, that is called reduction. Now historically, you might think the word oxidation has something to do with oxygen, and it does. We'll talk about that later. But here's how the terminology works. Okay, so here's how we would kind of diagram the reaction we just saw. We'd say iron went from 0 oxidation state to positive 4. Okay, and by definition, I put a little bracket here. That process is called oxidation. And diagramming the oxygen, it went from a 0 oxidation state to negative 2. That process is called reduction. So we'll use these brackets to kind of label what's going on. Now, here's some really weird terminology. Okay, look at the iron. Okay, now the iron gave electrons to the oxygen. Iron made the oxygen become reduced. The iron went from 0 to negative 2. Because iron was the agent for causing what happened to the oxygen, it's called the reducing agent. So the word agent is not what happened to it, but what it does to the other chemical. Okay, on the other hand, what happened to iron? Iron lost some electrons. Who grabbed the electrons? Who caused the iron to be oxidized? The oxygen. And for that reason, oxygen is called the oxidizing agent. That's probably where the word oxidation came from. They did a lot of experiments with oxygen, and it kept oxidizing things, so they call it the oxidizing agent. Now, I know students have trouble with this sometimes, so here's kind of a little trick, okay? If the iron is oxidized, it's the opposite kind of agent. If it's oxidized, it's the reducing agent, okay? And if the oxygen is reduced, it's the oxidizing agent. Okay, let me show you a couple of uses of this idea. Let's say you're working in a giant chemistry lab. Your job is you're a chemist in a giant laboratory. In that laboratory, you're probably going to find a shelf that has oxidizing agents and reducing agents. Now, let's say you want to do the reaction where A plus 2 becomes B plus 1. You want to reduce A. So what do? You grab something off the reducing agent shelf. Now, you don't care what happens to the chemical. The idea is a reducing agent will do the job for you. It'll reduce the chemical. Okay, example number two, you're driving down the street in your Rolls Royce. You're behind one of those tanker trucks, and on the trunk it says danger oxidizer. Oxidizer is the industrial word for oxidizing agent. And let's say the truck springs a leak and this oxidizing agent goes on your car. What's it going to do? It's going to oxidize your car. You could care less what happens to the chemical, you care what happens to your car. So an agent tells you what it's going to be doing to you. Now, in order to do oxidation reduction problems, you have to be able to assign oxidation states to the chemicals. Now, textbooks usually can take about 4 or 5 pages to explain this. Well, through the use of teaching, I've actually narrowed this down to just a few simple rules, and I had to give them some kind of name, so I decided to call them Berg's rules of priority. And I'll explain the word priority in a moment. Okay, so let me go through these simple rules with you. Rule number one is an element all alone gets a 0 oxidation state. So in this reaction I've shown you zinc is alone, it gets a 0. Now it's true there's 2 hydrogen atoms here, but it's still the element hydrogen alone, it's a 0. Now one big exception, let's say in this reaction it produces zinc plus 2. If they tell you that zinc, even though it's alone, has a plus 2 state, don't argue with them. Okay, so this is what's called an ionic equation. So you give it a 0 unless they tell you otherwise. Okay, next rule. Family 1A, when they're in a compound, you give them a plus 1 state, except for hydrogen. By the way, don't you love it when people give you rules and they give you exceptions? Sorry about that. Okay, so family 1A plus 1 except for hydrogen. Okay, I'll pick up hydrogen later. Now, group 1A, it's what you'd expect. When they're in a compound, they have a plus 2 oxidation state. Fluorine, you expect to be negative 1. Now, do you see this red thing here? That's supposed to be a greater than sign. It means the rules I just talked about are greater than, they have priority over the next rules. Next rule, hydrogen gets a plus 1. Now, I know it's kind of weird because I said plus 1, group 1A, except to hydrogen. It means group 1A has priority over hydrogen. I'll show you in a moment what that means. Okay, oxygen, next rule has a negative 2, but hydrogen has priority over oxygen. And then family 7A, negative 1. Okay, I'd like to now show you these rules in action by looking at some examples. So example number 1 is, let's say you're trying to analyze the compound lithium hydride, LiH. Okay, now who has priority, lithium or hydrogen? Yeah, lithium has priority, gets a plus 1. Now you always have to figure out the last chemical. So lithium gets a sign, hydrogen gets a question mark, but to make this thing neutral, yes, you'd have to agree hydrogen would have to be a negative 1. So what it means is hydrogen normally would be a plus 1 unless something forces it to be something other than that. Now these rules also give you some predictability. Okay, now minus 1 is not a very stable state of hydrogen. You would not want to hold lithium hydride in your hand because I guarantee it's going to react somehow. So lithium will become its normal state plus 1. So it gives you some predictability. Okay, let's analyze water. So between hydrogen and oxygen, hydrogen has priority, it gets a plus 1. Oxygen gets a question mark. Now notice that there are 2 hydrogens. Now here's how I want you to think about this. We'll figure out the individual states on the top. We'll do our calculations, our figuring on the bottom. So hydrogen has a plus 1, but there's 2 of them, so we have a total plus 2 charge from all the hydrogens. It's a neutral compound, so the charges have to add up to 0. So look at the green. The green is our conclusion. To make this neutral, to make this 0, the oxygen must have a negative 2 state, so you write a negative 2 up here. Okay. Now, it's the numbers on the top that are really important for balancing, which we're going to get to later. So our figuring goes at the bottom, but it's the numbers at the top we're really after. Okay, let's look at hydrogen peroxide. So hydrogen has priority, gets a plus 1. Oxygen gets a question mark. Okay, now, hydrogen has a plus 1, there's 2 of them. So we have a total plus 2 charge. Charge is supposed to add up to 0. Conclusion, math fans, yeah. So we need a negative 2 charge contributed by the oxygen, but there's 2 of them. 2 into negative 2 means each one is in a negative 1 state. Okay. What do you think is more stable, water or hydrogen peroxide, and why? Okay. The answer is in water, they both have their normal oxidation state. In hydrogen peroxide, oxygen's a negative 1. That is unusual. Oxygen is normally a -2, so your predicted hydrogen peroxide will be unstable. In fact, it'll actually react to go and form water. Okay, KMnO4. Okay, so K, potassium has priority as a member of family 1A plus 1. Oxygen, next priority -2. The last chemical can never be figured out. It's the one that gets the question mark. Okay, so here's the results of this. Okay, potassium has a +1, so we get a +1 there. 4 oxygens give us a total -8. The charges have to add up to 0. So math fans fill in the blank. Yeah, the green tells you the manganese would have to be a +7. And there's 1 manganese to carry it, so it has a +7 oxidation state. Now let me change the problem slightly. Let's say it said KMn2O4. Well, you still need a +7 total, but you divide the 2 into the 7, and each manganese would be a +3.5. Can you have fractions of oxidation states? Yes, you can. They're rare, but they happen all the time on Berg exams. Okay. Now, oxidation states are really a way of bookkeeping, a way of telling where the electrons are. So a 3/2 would mean the electrons move halfway somewhere. So don't be shocked if you get a fraction sometimes. Okay, last one. Okay, so SO4. Now, do you see that -2 there? Wasn't Berg nice? He was telling me the charge in the oxygen. No, no, no. I really should have a bracket around this whole thing because the SO4 totally has a -2 charge. It's actually an ion. So how do you treat ions? This way. Oxygen has priority -2. Sulfur gets the question mark. Okay, now here comes the work part over here on the right. Okay, so the 4 oxygens are giving you a total -8 charge. Charges have to add up to -2. So look at the green number. Yeah, the sulfur must be a +6, so this adds up to -2. And so there's 1 sulfur that's going to have a +6 charge on it. Okay, so now I'll pronounce you semi-experts at the rules of priority. And you might want to keep this page out because we're going to use this to do some balancing in the next pages that are coming up. Okay, I'm going to teach you 2 methods of balancing. And the first method is called the oxidation number method. Okay, I'd like to work with you on balancing the equation Al plus O2 gives you Al2O3. Now notice in red, I marked the oxidation states you get right off of the rules of priority. So aluminum all alone, L alone is a 0, L alone is a 0. Over on Al2O3, oxygen has priority, -2. Now -2 times 3 gives a total -6, so the aluminums must total a +6. Okay, but there's 2 aluminums, so each one would be a +3. So first step is you got to figure out the oxidation states of everything. That's step 1. Step number 2 goes like this. Aluminum went from 0 at the beginning to a +3. That is oxidation. Okay, oxygen went from 0 to -2. That is reduction. Now, I want you to mathematically summarize with me what happened. Okay, so aluminum went from 0 to +3. That's a change of 3 electrons per aluminum. Okay, you can write this negative if you want to or not. It really is not important. Okay, now in the case of oxygen, it went from 0 to -2. That's a change of 2 electrons per oxygen. Okay, next line goes like this. This is a critical line. We're trying to get the electron exchange equal. There has to be conservation of electrons. So electrons by aluminum must be equal to electrons gained by oxygen. Now, think in terms of units. I have electrons per aluminum times so many aluminums. So in terms of units, this will give us electrons. It'll be electrons lost. And over in the case of the oxygen, we have the units electrons per oxygen times oxygen will give us electrons that are gained. Now, the key numbers are the red boxes. How many aluminum should we take and how many oxygen should we take so the electron exchange is equal? Now, I'm really asking you this mathematical question. 3 times equals 2 times okay? Now, what works a lot is you notice you switch the numbers. If you take 2 aluminums and 3 oxygens, 3 times 2 equals 6, and 2 times 3 equals 6. Now, you see those red boxes? I want you to think of those as if statements. If we can really do this, then the equation will be balanced. If we can take 2 aluminums on both sides and 3 oxygens on both sides, we'll have the equation balanced. Let's try it.